Good afternoon. Hopefully today's lecture will demystify the connection between Bluespec programs you have been writing and the hardware, actual hardware that is generated. There is extremely tight coupling, and even though you don't draw this kind of hardware by hand, it's kind of important to understand the connection between the two. Because as you write more and more complex designs, you will move away from hardware, but you are always at some abstract level, you have to have a concept of what's going on underneath. This is the same kind of analogy one may draw when you program in high level languages. You don't worry about what's happening at the assembly language. But of course, there is something going on at that level too, and sometimes when it comes down to questions of efficiency, sometimes we have to go down to that level. But understanding the connection that ultimately any high level language is translated into a lower level machine language is a very important concept to understand. Similarly, in case of hardware description languages, it's very important to understand that we may have a very high level language in which we are expressing designs, but ultimately they are being translated into actual hardware. So that's the goal of this lecture today. So some of the examples I will do, you have done them before. The idea today is to demystify the hardware generation underneath it. So let me start out with interfaces again, that whenever we have a hardware module like GCD, it has two methods, start and get result. And start has two inputs, A and B, which of course I haven't written here, and an enable signal and a ready signal. And similarly, get result has a ready signal coming out, yes, result is ready, and when you pick it up, you have to enable it. So then get result will be given to you at that point. Okay, so this is what is expressed in the interface method also. So first thing you have to understand is inputs and outputs of a module are completely defined, in terms of types, right? So the interface is the type of the module. And once you know the interface, you will know every input and output wire that is going inside and coming out of it. Okay, so nothing in the implementation changes, the wires that come in and out of the module, and that's the property you want. You want this black box model. You want to use this module without having to worry about, how it's connected internally. So how do we know this? So for example, a read method has no input wires, right? An action method has no output wires, and you can see it in case of this start method. It's an action method, right? So it has two inputs as specified by the action interface, A and B. So each of these things will be 32 bits wide. And then because it's an action method, it has an enable wire going in. And because all methods have some ready signal coming out, so you have that green wire coming out which says I'm ready. You can enable it only if it is ready. This is a very high level protocol that will be implemented. Same thing is true for get ready. It's also an action method, right? Some value comes out of it and you have to enable it in order to get it, but you can enable it only when the ready signal is true. So this is the reason why we figure it out. An action value also has some data value coming out of it. So it will take you just 30 seconds to realize that if I write down the interface, you should be able to write down exactly what wires go in and out of this module. Okay, so this implementation was discussed in the recitation. It was supposed to be discussed in the lecture, but I didn't manage my time properly. So here is the implementation that was given to you, and this is a refrain. Anytime we have to write a module, we look at its interface and we figure out what are the methods, right? And how do I know the method? So if it has start method and get result method, I must define these things. And what is the guard for this method? Well, that partially depends upon the state. So we have, in our implementation, we have declared that we want two registers to hold the values, right, of A and B, which will be X and Y in this case, and we're going to have a separate flag, 1-bit flag, which indicates whether the module is busy or not. So initially it's not busy, that's why it's initialized to false. So based on that much information, you know that you can start it only when the module is not busy. Okay, so that's what it says here. This is going to be the guard signal, that is the green signal you were seeing outside, that corresponds to this thing. All right, and similarly here, when is the result ready? Well, the module must have been busy and x is value 0, so when x goes down to 0, that means you're done computing. The only reason I'm checking busy is, well, we start out with x equals 0. You haven't even put in anything, so let's just assume that it has to be busy before, the result is meaningful. Okay, and then at that point, we can easily write down the content of this. This is pretty trivial. X gets A, Y gets B, and busy is marked as true. And similarly, when you do result, when you pick up the result, you mark busy as false, and you return Y, whatever the value in the Y register was. The heart of the computation here, exactly how we compute GCD, is embedded in this rule over here, rule GCD. And I won't go over the details of this, but this was the main thing. If x is greater than or equal to y, then you subtract. Otherwise, you swap the two values in it. And last time you saw exactly how this swap works in terms of timing, because we are always reading the old values from the registers. And when we update whatever value the register gets, you can only see it in the next firing of the rule, in the next cycle of the system. All right. Now let me show you the power of abstraction. So we have defined this interface for GCD, and what I want to do is have another implementation of GCD. And furthermore, I want to use the GCD modules I have already defined. So the one I defined, I called it make GCD. Now this one I called make what? Oh, I haven't given it name yet. We'll call it some other name, right? So we are making a new module which is going to have much, much higher throughput. Why? Because inside it, I'm going to instantiate two GCD modules which you already know how to make, right? I mean, you have just made it in the previous slide. You know how to make a GCD module. And what I can do is, when a request comes in, when you want to start it, let's just take turns. So first one starts GCD 1, the next start will go to GCD 2, the next one will go to GCD 1, the next one will go to GCD 2, etc. Yes, very simple policy for using these two modules. And how do I collect the results? If the first one had gone to GCD 1, then I want to pick up the results from GCD 1, and that's being encoded using this turn output slide. So whose turn is it? So turn input tells me at the input time whether I should use this one or the other one. And similarly, at the output, I have turn output, which tells me whether I should pick up the results from the GCD 1 or from GCD 2. And there are a couple of things I want you to notice about this, is that it has exactly the same interface as the original GCD, right? So start and get result, you can't tell from outside whether I'm giving you a fast one or a slow one, right? And notice, in implementation of GCD, I'm using a slower GCD inside it. So you are really getting some feel for the power of this abstraction in this. And as I explained, turn I and turn O are used to direct the input or to pick the right output out of the results that are being computed. Now, can you write such a module? Can you write this super duper fast GCDB? This will be your intellectual property out of which you can make millions of dollars. Yes? How many people feel they can write it? Very good. So I think it's not so difficult to write it. Let's try it. So this is our overall picture of it. The interface is exactly the same. And what does interface tell me? Immediately that I have to specify the start method and the get result methods. Yes? The guards are tricky in this case, right? Because we have two of them going, so both of them have to be busy before something will happen. Let's see how it goes. So first thing I have to do is when I instantiate the state, I know I need two GCDs. Okay, so I say make GCD, I'm calling it GCD1, say instantiate it again. Remember our left arrow is always, the single left arrow is always an instantiation. So instead of instantiating a register, now I'm instantiating the GCD module itself. Completely legitimate, right? And by the way, the name of this one is make multi-GCD. So this way you know whether you're talking of the slow one or the fast one. This will be the fast one, right? We have given it a new name. Okay, but notice the interface for both of them is the same, GCD, because GCD was the type, the interface definition of this module. Now we also have these registers, turn I and turn O, which are simply, one-bit registers, so we can instantiate them and initialize them to false. Everybody is with me in terms of what is the purpose of these registers? Turn I will help me decide what? Yes? Not a difficult question. You have two GCD. Turn I helps me decide which GCD to use, right? If it's, either you will use one or you will use two, and that's a convention. Same thing is true for, yep.
Maybe this is a very pedantic question, but what if both internal GCDs are busy?
Very good. So I'm coming to those questions, right? So let's see. Let's just first try to write it down and then we'll see if it's going to work or not. Okay, so what do I do to start it? Does this make sense? If the turn is true, start GCD1, otherwise start GCD2. Make sense? So when can this rule fire? Sorry? It doesn't make sense? Sorry. Oh. Why can't you start it? When can you start GCD1? When it's not busy, right? Which is internal affairs of GCD. Outside, we rely on the fact that every method has a guard. So we will have a way of detecting the guard of GCD1 start method, right? And if the turn is for GCD1, we go and check if that is true or not. I will show you exactly hardware will do this, right? But remember, we have enough information because I have shown you the interface. GCD1 is generating a guard, right? And based on that guard, this rule, this method will either fire or not fire. If both of them are busy, what will happen? Right, so if it is turn 1, right, if it's turn of the first GCD, we have to make sure in our implementation that first is not busy. Or in our jargon, first is ready. If the turn is false, then we have to make sure that the GCD2 is ready. Okay, that's all we are doing. So does this definition make sense now? So it has implicit guards. Its guards are being derived from the guards of the things you're calling underneath. What about get result? It returns a 32-bit quantity. Yes? If the turn is for this one, For the first one, then you go and say get result from that one. Otherwise, you get the result from the other one. It's absolutely straightforward, right? If it's this turn, then y gets get result from GCD1, right? That's what is written over here, that if turn 0 is true, then you get GCD1 dot get result. If it is false, then you get results from GCD dot get results. You can ask the same question again. Yes?
Why is y getting instantiated?
No, it's not instantiation. Sorry, this is a syntax thing. Left arrow, single left arrow is used for two different purposes. One is instantiation, and the other one is kind of. How do I know whether I use left arrow or equal sign? Sorry? When you call an action value method. Action value method causes some change in the state as well as it returns a value. So if it's just changing the state and not returning a value, you just write down the name. You just write down f.dq. But when it's returning a result, then you have to say y left arrow, whatever, right? So in this case, that's the get result. Is this point clear to everyone? This is, okay, so let's go over it again. What is the type of get result?
32-bit value.
That's the value of the output value, you're right. But what is the type of the method itself? It's written at the bottom. It's an action value method. The moment you see the word action value, what does it mean? It's going to change the state. It's going to return a value. Whenever you call an action value method, you will always use the left arrow with a single something. Is it clear now? Okay. So, yes, language is overloading the meaning of left arrow. Left arrow most of the time stands for instantiation, right? Instantiate me a GCD, instantiate me a register. But when you have action value methods, then again we use the same arrow. Yes?
Why do we care about the difference between what kind of method is returning the value when we're trying to assign?
So for example, if I had f dot first, right, I would have written an equal sign. Y would have been y equals sign f dot first, if it was a Q or something.
Yeah, why do we care about that difference?
Very good question. So who's going to tell me the answer to that? Why do we care that it's a action value method versus it's a pure method? You know, it doesn't do anything to the module. You see, think of it like this. Suppose you're dequeuing. If you dequeue twice, you expect something more to happen, right? But if you do first from a queue twice, you know, you expect to get the same value unless somebody else did dequeue or enqueue or something, right? So first is a pure read method, pure value method. It doesn't affect the state. And it's very important for us to keep this thing in mind. Is it affecting the state or not? If it is not affecting the state, then we can use equal sign. If it's affecting the state and returning a value, then we always use single left arrow. Extremely important to keep this distinction in mind. Actions versus read methods. Read methods are just observations. Something is going on in the module, you put your telescope, you say, that's what happened over there. Action methods actually are poking it, they're doing something inside which is not visible to you. The effect of action method is only visible to you via read methods when you go and apply something or through other action value methods. Okay, so my goal today is to teach you enough so that you can go and draw the hardware diagram for both of these GCDs. Okay, so that's what you will do tomorrow's recitation or something in the take-home example. But I want to do it systematically so that I'll do simple examples, and then you say, oh yes, I can do GCD. I can build a fast GCD too, and understand every bit of hardware that is being generated. So how does hardware synthesis work in Bluespec? First, every module represents a sequential machine. Never forget that. Every module represents a sequential machine. It may be very trivial or it may be complex. It always represents a sequential machine. The most primitive module that we deal with, or most primitive sequential machine, is a register. So by our definition, even the register has to be thought of as a module with some interface methods, etc., which were discussed in your recitation, but I'll show it to you again in a second. Implementation of registers is outside the language, so we never will tell you exactly how register is being implemented, but we have hopefully demystified it for you by saying that, oh, it's actually a bunch of D flip-flops with enables, but they share a common enable signal. But you will not go down to that level of implementation yourself. And how is the register bit width derived? Because you always, even register holds values of certain type. So you may explicitly say it says 32 bits, or you may say it holds things of type T, then we have to go and look at type T and see how big is type T, right? And that's the amount of register space that will be allocated. That's the kind of register you will make. Okay, there is never the case where the system, where the compiler will go and introduce a new module in your system or instantiate a module without you knowing. So anytime you see a register or a module in your design, there is some code line somewhere where you explicitly instantiated it. And if you forget to instantiate it, no hardware will be generated for that. One-to-one correspondence. Every piece of hardware, every piece of stateful hardware, registers, modules, have to be instantiated explicitly. You saw that we instantiated 2 GCDs and 2 registers in that case, and there is no other stateful entity in that module implementation. That's the end of the story as far as we are concerned. And as we have said repeatedly, interface tells us everything about the input and output wires of a module. Now, this is the part that people find slightly mystifying. You write these big rules, GCD rule or some method. They only define combinational logic. So in some sense, rules and methods are the glue by which we connect these stateful things. So we have modules of various sorts, right? Registers or more bigger modules, and we have only one method of connecting them. And that is, we'll use a rule or a method to call them, and then things will get connected. And that's the demystification I want to do for you. That we can make a module, and then we can write rules which can connect these modules, and it's recursive. We can keep building bigger and bigger things this way. The resulting hardware is a collection of sequential machines, and this is the point I want to emphasize. Even though we say in the jargon that, oh, any piece of hardware is a sequential machine, if you thought of your computer as a sequential machine, your head will explode, because there are so many states that you won't be able to make head and tail out of it, no sense out of it. So what we do is we always think of complex pieces of hardware in terms of collection of sequential machines which talk to each other in some very dignified way, in some very restricted, in some very well-defined ways they talk to each other. And our design methodology has to support that. We should be able to design modules and then connect them together in some meaningful so that's the closure, and that's how we will get bigger and bigger and more complex pieces of hardware. And it is precisely this property that lets you design extremely complex hardware by the end of this class. You'll be surprised, even in the next, by homework 5, you'll be doing things, you say, whoa, I have a working computer, right, with me. Let's revisit the register, which was discussed in the recitation. So register has 2 methods, read and a write. And if I was to actually write down the interface, this is how it will be written. It's underscore something something, because these are systems names, and you are not allowed to use some other names for this register unless you define it yourself. So because registers happen all over the place, there is special syntax for using registers. So instead of writing x dot underscore write e, we write x gets double arrow e. But these two things are equivalent. Okay, and similarly, when you have to read it, instead of writing x dot underscore read, we just write x. So whenever you see x on the right hand side, you're always reading a register. When you write it on the left hand side, that means you're about to assign to it. Very good. Oh, yeah, one more thing about this. So registers have, either you can say it has no guards, or you can say it has true guards. Guards are always true. Register always holds a value. You can read it any time you want. And therefore, we don't show the guards, right, of this. True, because we'll be, as you will see with guards, we just keep conjoining them. And true, when you conjoin it to anything, doesn't do anything. So registers have guards too, technically, but they are not drawn in the pictures. But they have enables, right? So you cannot write into a register unless this red signal is on. It says, yes, go and write something. Very good. Yes?
One way we have of defining registers is to define them with an initial undefined value.
Yes?
Is it okay to read an undefined value
No.
register?
If you try to read undefined values, bad things will happen. Most of the time, system will catch it, right? Right? I don't know if it catches it 100%, but you should not do that. Very good. Yes?
Are we allowed to do this underscore write underscore read and things that we
Yes,
create?
it'll work.
Okay.
You can use that. Please don't do that, because that you'll just make your code more unreadable. Right? Okay. This is just for pedantic reasons, that register is indeed a module with a proper interface, and you can think of it as having guards and everything. Okay. So let's see what is the connection between a module and a sequential machine. All right. So suppose I have some module M, and it has two methods. Even I can't read it. Something, oh, I see. I wrote it sort of flattened it, something. F and G methods it has. All right. So just by looking at the picture, no, actually not by looking at the picture. If I go and examine the module, what have I promised you? Every register would have been explicitly declared. So I can open up the module and I say, oh, this has registers, whatever registers I've shown you with their sizes, and I know that it's my job somehow to supply the data and the enable signal for every register. So if it's a sequential machine, so these are declared in your module, and they're all controlled by the same clock, right, because we are designing single clock circuits here. And remember, in a sequential machine, so you have state elements, and then you have combinational logic. And what is the purpose of this combinational logic? To go and generate the register values and the enable signal. For every register, for every cycle, data value and the control value has to be generated. The data value may turn out to be don't care if enable is false, right? If you're not going to store it, then it doesn't matter what that data is. But generally, your responsibility is, or compiler's responsibility is, that it will generate these registers, then there will be combinational logic generated, which feeds all of them. Okay, next point. This combinational logic is going to be derived by the rules and the methods you write. That's what I'm going to demystify for you. What is the connection between this combinational logic and the rules and methods you write? Okay, and sequential machines have inputs and outputs. And who defines the inputs and outputs? Interface, right? So the moment I tell you the interface of a module, I already know the input and output wires of this module. So if somehow I can generate this picture, given a module implementation, then we are home. Then I have shown you that for every module you write, here is the corresponding hardware. Is the high-level plan clear to everyone? Right? You're going to give me a module implementation, interface definition. You claim that this implementation implements the interface. And today's lecture, what we are showing is how to take these things and actually generate circuits from it. All right. So some, just before I start, in the subject we study only single clock circuits where all registers are connected to the same clock, and therefore we will not show the clocks. In fact, you have no control over this clock, at least the level at which we are teaching this class. There is nothing you can do in Bluespec, the Bluespec that is being taught to you, which will let you generate multiple clocks. So therefore, clocks are beyond us. This is a very good property of Bluespec, that if the whole circuit uses only one clock, clocks never show up in Bluespec descriptions. Okay. Another thing to notice is Bluespec, the designs you write, the code you write, or the interfaces you write have no explicit, ready signals and enable signals in it. So they are all being generated implicitly. They are all being generated implicitly, and that's very, very useful. That's what we have to understand. How does that work? Okay, so here is my most real example. Does everybody understand this module? Module example 1, let's ignore the interface issues right now. Its state is register X, right? You're making a register X, and it has a method called F, which assigns some expression E to X. Is this module clear to everyone? By writing E like this, I'm saying some expression, some combinational expression. Yes?
Does that expression E involve the input A?
It can. It can involve many things, right? Okay, so whenever I use this italic sign, this is generally followed in programming languages, that it stands for an arbitrary expression over there. So how will I compile this? What is the hardware generation corresponding to this? Yes? I have declared a register, so we go and make a register X. Allocate me a register X, it will have an input data and it will have an enable path corresponding to it. Are you with me on this? Very good. Now let's focus on this action method, F. Does this make sense? What is this saying? You take E, which is a combinational expression of some sort. It may be A plus 1, it may be A plus 50, it may be A squared, whatever, right? It may be A plus X. Sorry, it can be A plus X. You can write down the combinational circuit corresponding to it, and that's what is shown in that cloud, E. And the only possible input in this case I've shown is A, but in fact X can also be an input going into it. Now, when does this assign X to E? When does E gets assigned to X? Whenever you execute this method, right? And how do you know you are trying to execute this method? Because it has an enable signal. So I took that enable signal and passed it on to the enable of the register. So whenever you execute this method, value E will get assigned to register X. Therefore, my whole design becomes like this. Yep. Sorry? So of what is the meaning of enable for a register. So remember, in our basic definition of a register, we are only dealing with registers with enables. So anytime you want to write into it, you have to enable it, right? Write enable. So you think of it as a write enable. And in this case, it should be very obvious to you that you have to write in the register if the method is being executed. So enable of method is the same as the enable of the register. Please notice that stuff that is drawn in the box is purely combinational circuit. What knowledge did we need to write this box, to derive this combinational circuit? We only need to know, the body of the method in this case. X gets E. But the actual assignment is outside, So all we have responsibility for is, I have to generate an enable signal for X because X is being assigned E. Let's look at a few more examples. How about this one? How many registers should I allocate? 10? 1, right? So just like before, we have register X, and look at the method here. What is the method like? In this case, if B, then X gets something. Interesting, so what that means is I have to compile the combinational circuit for E, and I have to compile a combinational circuit for B, and combinational circuit for B will generate a Boolean, because it's a typed language, so if you're using if there, it must be generating a true or a false over there. But now comes the interesting part. How often do you assign in this register? How often is X assigned? Anyone? How often are you going to assign in X? Only when B is true. Not every time the method is called. Method has to be called and B has to be true. Does everybody get it? Right? It's a conditional assignment. The condition has to be true. And therefore, you see that picture. You see here that I took this and I compute B, and now whatever the output of B is, which has to be 1 bit, I'm ANDing it with the enable signal for the F method. And I take these two things, and that becomes the enable signal for X. Conditional assignment. Yes?
Why not make it a guard?
You could have. That would be a different program and different hardware. We are coming to that, right? So I could give you the exact algorithm for generating hardware, but instead I want to keep it at an intuitive plane so that when you see something, perhaps you can just look at these pictures and say, I know what I have to do, even though your example may be much more complex, right? I'll come to guards. Okay? So to complete it, I just connect those wires. Yes?
So what happens if E takes a really, really long time, but B doesn't? So your enable signal gets through before your data is ready?
Never have to worry about such things because the clock period in this will be determined at a later stage by the maximum, the longest combinational path between two storage elements, right? So that part is invisible to you. You make changes in your Bluespec program to indirectly affect that. You can directly never control the clock. So never have to worry about those kinds of races at this level of design. Here is my third example. It also has only one register, right? But it has a slightly more complex method call. And what is the method call in this case? If B, then X gets E1, else X gets E2. in every case, the method, you're only defining combinational logic. State logic has already been defined. It's register X. Now, how often do you store in X in this example? How often do you store in X?
Every single time, yeah, every single time, because if whether or not B is true doesn't matter. X, something will be stored.
Does everybody get that? That regardless of whether B turns out to be true or false, you're still going to enable it. So enable part is simple, but the data part, there is a selection going on. Either you'll be storing E1 or you'll be storing E2, and I hope by now all of you know this mux structure, right? Given a bit, it's picking up between E1 and E2, and B is just another condition. So it doesn't matter how big the circuit B is, ultimately it generates one bit, true or false, which will select this mux. Are these examples clear to everyone? The thing to remember is all the state elements were explicitly declared. In this case, it was trivial, it was just X. And method only generated the combinational circuit, but it generated a combinational circuit which had a value for X as well as the enable signal for F, for X. Okay, so now let's look at a slightly more complex example. So what's happening here? You have a module which has one register X, but it has two methods, F and G. And what are these methods trying to do? They're both trying to write in X. Yes? Both are trying to write in X. All right, so part of it is very easy based on what we have done so far. You know, I generate the code for F and I generate the code for G. The question is, what goes here? Mux, right? But why can't I just put a mux right in there? Do you know how to select it? If suppose both of them are true. Sorry? They can't be true at the same time. If they're true at the same time, you have a bad design. Right? Can't be assigned at the same time. So this is something that Bluespec compiler is very good at. Right? It will never ever let you do that. If it gets two things which are trying to assign in the same thing, then it will say, sorry, there is a bug in your program. Go and fix it. Compiler has to make sure that both F and G can't be enabled together. So this is now problematic. I have this module and I'm trying to generate some code for it. But suddenly, these enables come from outside, right? These enables come from outside, and my code is correct, generated code is correct, provided somebody generated the enables properly. So there is some responsibility being passed out, and compiler is very, very good at that. You know, it will just automatically move it up. So how do we express such design? This is what we'll do. We will use this kind of a mux. So the idea here is this, I mean, you can understand it. You know, it's saying that x1 is meaningful only if v1 is true, x2 is meaningful only if v2 is true, right? And then the output will be v1 or v2, and you're selecting the data output correctly as well. But somewhere there is a restriction that both better not be true. So we will generate this kind of circuit for the example I showed you, and somewhere compiler has to remember F and G better not be true together, because better not be enabled at the same time. How does that happen? That's where you have to get into the recursive aspects of it, which I will show you later on, not in today's lecture. Okay, so what does that structure look like? You know, this is the structure you have seen from lecture 3 or something, and this will be repeated n times. This is just to emphasize, never forget, muxes take a lot of area, right? In software, you're used to writing variable x. Here, if variable x is 64 bits wide, a lot of hardware is being generated. So muxes in hardware are not free. Okay, so now we have additional problem. We have this problem when synthesis of multiple sources for a register assignment. So you have F and G, you know, so we have, sorry, this is the same one. So this is what we will generate for this. And remember on the side that both F and G are not true at the same time. The high level point here is this circuit is correct only if something is assumed about the environment. And what is being assumed about the environment is F and G cannot be enabled simultaneously. So this condition has to be taken all the way up, and compiler has to make sure that that is indeed the case. Let me do another example for you. FIFO. Very quickly, let's do it. So this is the code you have seen gazillion times by now, right? One element FIFO. And you can draw all the wires in it very, very simply just by looking at the interface method of this. What I want to show you here is how the circuit is generated step by step. Okay, so we have this code over here. First thing is I/O interface, because that tells me the input and output wires. So we have NQ, DQ, and first, and these are the wires that are going in and out. Yes? Good? Instantiate state. What are the state elements in this? You have D and V, right? So you will have two elements like this. Easy. Now generate the method for me. Generate the code for NQ. Oh yeah, we have to generate muxes here too. So D, we don't have any muxes. Why? Because only one method writes in D. V, on the other hand, two different methods are writing in it, so there will be a mux needed. Okay, now let's generate the a code for NQ. So what does NQ do? Is assigns, what does NQ do? I can't read it. It assigns true to V and the incoming data to D. All right. So data goes here and it will be assigned anytime NQ is true. And what about V? Okay, so it has to put V value, and that's what we want to do whenever we want to NQ. Does this look reasonable? This is the code for NQ. Now, when is NQ enabled? So this is where somebody was asking about guards, right? So the guard for NQ is not V. So therefore, we have to look at V, you know, take the knot of it, and where should this be connected to? The green part, right? This is the guard, this is the ready signal for NQ. Can you do DQ for me? DQ is so trivial that it's almost harder to do it. What does DQ try to do? It tries to put a false value in V. All right, so we take the enable of this thing, and what is the guard for DQ? V, right? So does this make sense? That the output of V is connected to the ready signal of DQ. First, what is the data for first? Output of D is the data for first. So therefore, you take this, and the guard is the same thing that was for DQ. Can everybody see this, that I did it methodically? I took the definition of FIFO. Admittedly, it's a very simple example, but believe me, this will work for you regardless of how complex the design is. Start out with the methods that will define the input-output wires, instantiate the state, and implement methods one by one, and if there are rules, implement the rule too, right? In this, yes?
Is there a good strategy for choosing which methods to start with first?
So actually, just hang on a second because I need to show you one or two more slides here. I have redrawn that picture here. This is how conventional people would do it, right? If you were not thinking in terms of methods, you know, you will say, oh, these are the input wires, these are the output wires, and I'm a happy man. Now I have a sequential circuit for FIFO, which looks like a conventional sequential circuit. So you may think that I was doing something very pedantic, but really there's a method to this madness, and it will help you draw much, much more complex designs together, as opposed to doing something arbitrarily. I also want to remind you of something that people are in love with: state machines, next state transitions. And if I gave you the assignment of writing the next state transition for FIFO, you'll be able to do it, but it'll be so tedious. You'll be complaining to all your friends, man, you know, this stuff is really, really bothersome, right? And not only that, you will find many, many cases here where it's illegal inputs in this. The next thing is, I just want to emphasize for you that there are constraints that have to be obeyed, which I haven't shown you. That you should not enable something unless the ready signal is true. Correct? Right? Otherwise, the whole system will break down. And here is the trivial example for this. So I have this rule which is just streaming through this combinational function f. And you will see that you have this and you have f. You can compile all this, and you can connect the data path very easily for this. But now, when can this rule fire? When can this rule fire? Lots of things have to be true. Input Q must have the first and DQ ready. Output must have the NQ ready. So you will just bring all those things here into an AND signal, you know, and you're connecting them all together. And only if all these things are true, then you can enable it. Then you can say, oh, the output of this is connected to, you can actually NQ something there, and you can actually do some DQ over there. Believe me, this is all you need to know in order to implement that GCD and the fast GCD. You should be able to understand every gate that will be generated in that example, and that's exactly what I want you to do in tomorrow's recitation. All right, I'll stop here.